All right, this is part 2 for Algebra 2, Day 2, looking at factoring polynomials to identify zeros. And this is activity 1, which starts on page 200 and, let me use a better pen, 276. Okay, so we were just factoring factor trees and looking at prime factorization of numbers. Now we're going to focus on polynomials. And I will review some of the factoring methods as we come along, but you should have already done some factoring in Opt 1. And one of those factorings is factoring out a GCF, or a greatest common factor. And when you're talking about polynomials, a greatest common factor, and this is important over here, greatest common factor can be a variable, a constant, or both. So it could be 3, or it could be 3x, or it could be 3x squared. It could be whatever it needs to be, okay? It could have a y in it. I don't know. There's lots of options. So we have these two students who are factoring out the GCF. And you always want to begin factoring any polynomials to look for a GCF, because once you take the GCF out, you can then see all these other things, all this other form of factoring that you know, and you break it down. And that's the first way to start, is always start with the GCF factoring, okay? All right, so Ping and Shalisha each attempt to factor 3x cubed plus 12x squared minus 36x by factoring out the greatest common factor. So let's take a look at their work. So we can see that Ping factored out a 3x. So what he saw was 3 goes into all three of the constants, or the coefficients, 3, 12, and 6, 36. And he also saw that they all have at least one x in them. X cubed is just x times x times x. X squared is x times x. And x is just, well, 1x. So he took out 1x. Shalisha took out the 3, but she did not take out the x, so she left the x's the same. So analyze each student's work. Determine which student is correct and explain the inaccuracy in the other student's work. Okay, so take a minute to write. Pause the video. Write out who you think is right, and then we'll go over it. So the person who is correct is Ping. And the reason that Ping is correct is because he took out the entire GCF, while Shalisha only took out the 3. Okay, so in your own words, you can write this down, why Ping is correct. And that is because he took out the 3 and the x. He took out the entire GCF, while Shalisha left that x in there, which was part of the GCF, okay? So now let's completely factor that expression, because he's not done. Okay, so let's go with Ping's 3x, he already took out. Let's focus on what we have left inside. Okay, so there's an error in the book. There's a minus, where it should be a plus. It should be a minus, but it's a plus, okay? So let me show you what I mean, and you can kind of fix it in your book. If you look right here, it says minus 36, but in the problems that they both did, they've changed it to a plus on accident. So we're just gonna fill it in with a minus. There's a mistake here. Maybe your book has it fixed. This is basically going off of what I had last year, so maybe they didn't get it fixed. So I wonder if they got it. Oh, they did fix it in yours. I see it. Okay. So they didn't fix it in mine, but mine's old. They fixed it in yours, right? There's a minus there. Okay, because that's important. Otherwise, you wouldn't be able to do much factoring here. Okay. I'll have to update my slides for the next videos I make because there's might be some errors. So this is a minus. I just noticed that. Okay, so that's a minus. Now we can factor it. Okay, so we've already got the GCF out. Now I want you to focus on what's inside the parentheses here. This is a trinomial. It's got 3 terms, and it is a trinomial of the form. So let me write down what this is. This is a trinomial of the form ax squared plus bx plus c. And a is equal to 1, which is why you don't see a number in front of the x squared. So if a is equal to 1, it's like the a is just not there. When we multiply by 1, it disappears, right? So now let's figure out what we have left to factor. To factor these, we do what's called a diamond problem. Well, this is one way to think of it, where we're trying to find a product of c and a sum of b. So c is my product. We want to find 2 numbers that have a product, that means multiplication, of that number. And b is my sum. So let's say I get d and e. Then this factors into x plus d times x plus e. So we need to figure out what 2 numbers multiply to make negative 12. That's my c here, negative 12. That's my product. And add to make 4. That's my sum. So think about all the numbers that multiply to make negative 12. One of them is going to be positive. The other one's going to have to be negative. And then, so let's see, 12 times 1, 2 times 6. Oh, I think I know what it is. It's going to be a positive 6 and a negative 2, because when you add those together, you get a positive 4. So this is going to factor into x plus 6 and x minus 2. And that GCF that we took out is still there. The 3x is still there. All right, use the factors to identify the zeros of 3x cubed plus 12x squared minus 36x. Okay, so now that we have it factored, this polynomial, we can graph it using the zeros. So let's review how we find zeros. Basically, if you pretend that f of x is equal to 0, and then we solve it. So there are 3 main factors here. We're going to use the zero product property, which says that if the product is 0, then they have to be 0, essentially. So I'm going to take each of these factors and I'm going to set them equal to 0. So we'll do 3x equals to 0. I'm going to, and then that's just 0. You divide by 3, you get 0. Okay. I'm going to do x plus 6 equal to 0. That gives me negative 6. And let's see if I can squeeze it in here. X minus 2 is equal to 0. Add 2 to both sides, you get 2. These 3 numbers are the zeros. Okay, so to sketch the graph, I'm going to have to put some numbers on the x-axis. They didn't put any here, so let's see, 1, 2. 0 is right here. We need negative 6. 1, 2, 3, 4, 5, 6. So here's negative 6. So I'm going to put some big fat dots here. I'm going to put a dot at 0, which is the origin, at 2, and negative 6. Okay. I believe you should already have learned in Opt 1 kind of how the degree of a third degree polynomial looks. and the leading coefficient kind of tells you which direction it goes, but I'm not sure if you do or not. But a cubic function will go like this if it's positive in the front, the leading coefficient. The leading coefficient is 3. And it'll look this way if it's negative. So to make the rest of the graph, we're going to make a little wiggle. I'm going to go up. I don't know how high. We don't have that information. Go back down, go back up. We don't really know exactly how it looks. This is a sketch. Okay? If we want to compare it to the real thing, we can go on to Desmos. We can see how it looks. So we can do f of x is equal to 3x to the third power plus 12x squared minus 36x. And you can see how it goes way up. I didn't go that far up. It goes almost to 150. But you could see that the zeros are at -6, 0, and 2. Those were the intercepts that we had. Okay, so in number 2, you're going to do the same thing. You are going to factor all of these. And you are going to sketch graphs based off of the zeros. Okay? To save time, I'm not going to go through these. Give them a try, and you guys should know where your answer key is so you can check your work for that one. Okay. I am going to jump around a little bit because I want to make sure that we cover everything, and I don't want this video to go longer than a half hour. So let's, I'm going to go ahead and we're going to talk about this question right here. Okay, so Tony and Eva each attempt to factor f of x is equal to x cubed minus 2x squared plus 2x. Okay. So let's look at what Tony did. Tony took out the GC of x and got x squared minus 2x plus 2. Okay. Eva took out the x, and then she took this thing, and she couldn't factor this. Well, he couldn't factor it either. He couldn't factor that expression. So he just stopped. What she did was she broke it down and solved it using the quadratic formula. Right? X equals negative b plus or minus square root b squared minus 4ac all over 2a. And look what she ended up getting when she did it. She got a negative under the square root. And that turns into an I. Right? Imaginary numbers. So the square root of -4 is the square root of -1 times the square root of 4. And the square root of -1 is I, and the square root of 4 is 2, which we can put in front. And that's how she got to I. Then she reduced everything by 2 and got 1 plus or minus I. So here's her factored form, x times x minus 1 plus I in parentheses times x minus 1 minus I in parentheses. Interesting. Okay, so the next question says, analyze Tony and Eva's work. If you consider the set of real numbers, who is correct? If you consider the set of complex numbers, who is correct? Well, which one has real numbers? Okay, Tony's has real numbers. Okay, so if we were talking about real numbers only, then Tony would be correct. Okay, if we're talking about complex numbers, Eva is correct. Now, there was an error on here, which I don't know if they fixed this. No, it's right. Okay, no, it's fine. An error, sorry. Ignore that. But I did switch them around, I think. Okay, using the distributive property to rewrite Eva's function to verify the function is factored form is equivalent to the original function. Okay, this is fun. This is a lot of fun. You're going to love this. Okay, what are they asking me to do here? Well, here's her form. I wrote it again. I'm going to FOIL or multiply the two big parentheses to each other, and then I'm going to distribute the x. Okay, so here's how I got this. This is like really complicated because there's three things. I'm going to start by distributing this negative for both of them. So this is going to be x minus 1 plus I. And this one's going to be x minus 1 minus I. And then I'm going to do a 3 by 3 square. I'm going to multiply using a grid, a table, because it's going to be a lot easier because there's three things in each. And I'm going to ignore this x until the very end. Okay, so I'm going to do x minus 1 plus I. Okay, and then along the top, I'm going to do x minus 1 minus I. Okay, now I'm going to multiply everything in. So x times x is x squared. Negative 1 times x is negative 1x. Negative I times x is negative, I'll just say negative I times x. I don't know what that is. And then I'm going to do the next row. X times negative 1 is negative 1x. Negative 1 times negative 1 is positive 1. Negative 1 times negative I is positive I. The negatives will cancel. Okay, now the last row. X times I, negative 1 times I, and negative I times positive I. So you kind of have to remember what I squared is. I squared is equal to negative 1. So if I do I times a negative I, it's like negative I squared. That's equal to negative 1, which is positive 1. Now you're going to see some stuff cancel. Like negative ix and positive ix, gone. They're opposites, okay? I and negative I, gone. Okay, now we can clean it up a little bit. We have, let's take everything out and combine like terms. I see some things I can combine. I have x squared minus negative x and negative x is negative 2x. And then I have a 1 and a 1. Remember, this is just 1. That's 2. All of that turned into x squared minus 2x plus 2. Okay, now there's one little, remember that x I ignored in the front? I'm going to now distribute that. That's easy. Distribute the x, and we get x cubed minus 2x plus 2x squared. X times x is x squared, and then plus 2x. And that was the original equation. Okay, so we do verify it, it is true. It's a rough one to multiply, I know. So what are zeros of the function? So the zeros of the function are pretty much the things after the subtraction sign, plus this x, there's nothing subtracting, so you can think of it as x minus 0. So my zeros are 0, 1 minus I, and 1 plus I. So that's looking at complex numbers and the zeros and their complex numbers. Now we can't graph those as x-intercepts at all. But we know that they exist. Okay, for number 6 here, you want to look at these and try factoring them, and if you get imaginary numbers, that tells you it has complex or imaginary factors. Okay, so if you can factor it, you can see that it has real zeros, real factors. Okay, if you can't factor it and you use the quadratic formula and you get imaginary stuff, that tells you they're imaginary factors. Okay, so that's how you do number 6. I'll leave that one for you guys. Okay, the last thing we need to talk about is just like some other types of factoring. So this is an activity 2. We're going to look at other types of factoring that you can do. All right, so this type of factoring kind of is using a method called chunking, okay? So you can substitute the common term with a variable like z, and then factor as you would any polynomial in a quadratic form, okay? So let's look at the example to see what they're doing. We have 9x squared plus 21x plus 10. 9x squared and 21x, you can both write in terms of like a 3x. So you can see if I took 3x and put it in parentheses and squared it, that gives me 9x squared. And 21x is like 7 times 3x. So what they're doing is they're replacing, putting in this 3x. It's got to be the same thing for this to work. Okay, so there's the 3x and the 3x. Then what they did was they replaced the 3x with z. Just a letter. They're just making it simpler with a different letter. Now this becomes one of those diamond problems we were talking about, right? Something squared plus some number times that variable plus a number. Okay, so 2 numbers that multiply to make 10 and add to make 7. Are 5 and 2. So they wrote z plus 5 times z plus 2. But then what they did is they were like, oh wait, we don't want z there. They took the z out and put back in 3x. This is a method for factoring. You can, if it doesn't work for every type of polynomial, but you can use it when it does work, okay? Let's look at one more. Use the chunking to factor and identify the zeros of this one. So we want to think of 25x squared as, well, it's something squared, and hopefully that thing goes into 20x. So 25x squared is 5x squared, and 5x goes into 20x 4 times. So we can write it as plus 4 times 5x. And then the minus 21 is just at the end. So then we can take the 5x out and replace it with some letter. They were using z. You could use w. It doesn't matter. We'll stick to z. So z squared plus 4z minus 21. Let's do the diamond problem. So we need 2 numbers that multiply to make negative 21 and add to make 4. Well, one of them is going to be negative, one of them is going to be positive, and it's 7, positive 7, and a negative 3. Now we can replace the z back with the 5x. Okay, it's factored. What happened? It disappeared. I must have undone it. Okay. So now they want us to sketch the graph. We're going to need to find the zeros. And to find the zeros, we're going to have to set this equal to 0. So we're going to take each of these and set them equal to 0. Because this is equal to 0 now. Add 3 here. Divide by 5. Subtract 7 here. Divide by 5. And those are our zeros. So 3/5. Just say it's there. -7/5. I'm just estimating. And it's a quadratic, it's a parabola, so it must go down and then go back up. Just a sketch, doesn't have to be perfect. Okay, so we have to look at perfect square trinomials and factoring by grouping. We'll do a couple of the problems from this section on those, okay? So perfect square trinomial is a type of factoring that you have to recognize a pattern, and that pattern is that the first and last terms are perfect squares. So here and here is what we're recognizing. And the middle term is equivalent to 2 times the product of the first and last term's square root. So you could see the A and the B, the product, and then it's always going to be double it, and it could be positive or negative. If you see a negative, that just means that there is a minus in the middle of your factorization. And if you see a plus, it just means it's plus. Okay? So you have to identify that you actually have the perfect square trinomial before you can just use it. Okay? So determine which of the following polynomial expressions is a perfect square trinomial and then write it as a square of a sum or difference. If it is not a perfect square trinomial, explain why not. Okay, so there it is again, right there. I'll write it again. So a squared plus 2ab plus b squared equals a plus b quantity squared, or a squared minus 2ab plus b squared equals a minus b squared. Okay? So let's take a look at this first one. We've got x to the 4th plus 14x squared minus 49. So is this a perfect square? And is this a perfect square? Well, x squared is x to the 4th, so that's a perfect square. Now, 49 is a square, but negative 49 is not a square. Notice in both of these, this has to be positive. If you put 7 here, that would give you positive 49. If you put negative 7, that would give you positive 49 also. So this one is not a perfect square trinomial. And that is because of the minus sign right there. Okay. B, 16x squared minus 40x plus 100. Okay, let's see. Got to check, is this a perfect square? It is. It's 4x squared. And 100, is that a perfect square? Yes, that's 10 squared. Okay, it's looking good so far. Now you check the middle. The middle should be 2 times 4x times 10. If you do 2 times 4x, that's 8x. 8x times 10 is 80x. Oh, it's not. Nope. Not a perfect square trinomial because that middle term was not doubled. That's really important that it's doubled. Okay, so not a perfect square trinomial. All right, let's look at C. Okay, 64x squared is 8x squared. Okay, it's a perfect square, and 4 is 2 squared. Okay, now we got to check the middle. Is it, oops, wrong thing. Let's try this. Take the 8x and the 2, multiply them together, and then double it. It checks out. That gives us 32x. Notice there's a minus sign. So now to factor it, let me get some room here. To factor it, it's going to have a minus in the middle. You're going to put the 8x here, and then remember it was a 2 squared and a 2. Now, technically this one does have a GCF that we should have pulled out. We didn't do that. If you took out the GCF, you would have taken out a GCF of 4, but it should still work. But we can leave it like that. We don't worry about, let's not worry about that, okay? All right, I'll let you do D on your own, the last one. Let's go ahead and talk about something called factoring by grouping. Okay, in a polynomial of 4 terms, you may notice that although not all terms share a common factor, pairs of terms might share a common factor. In this situation, you can factor by grouping. Okay, so let's look at Colt's work here. We had x cubed plus 3x squared minus x minus 3. What we're going to do is we're going to pull out a GCF from each pair. So from the first pair, it was an x squared, and we're left with x plus 3. From the second pair, you can take out a -1, and you're left with an x plus 3. Notice that each of them have an x plus 3. That's really important. If you don't get that common thing, the rest of it doesn't work. So notice what happened. Then it became x plus 3 out in the front. And this x squared minus 1 came from here. So let me explain that. It's like the x plus 3 was a GCF. In fact, you can replace it with like some letter. So instead I'll write it as x squared times, I don't know, a, minus 1 times a. So all I did was I replaced the x plus 3's with an a. Then from there you can take that a out. Oh, it's a GCF, and you're left with x squared minus 1. But then you put the a back, you get x plus 3 times x squared minus 1. And then the rest of it is they factored x squared minus 1 to get x plus 1, x minus 1. Okay, so this is just asking you to explain all those steps. But let's do one more where we have to factor by grouping. So let's do number 5. Okay, use factor by grouping to factor and identify the zeros of f of x is equal to x cubed plus 7x squared minus 4x minus 28. Okay, so let's do another one. We're going to take a GCF out of each pair. So the GCF of this one is x squared, because this one has x squared, this one has x cubed, which has an x squared in it. When you take the x squared out of x cubed, you're left with 1 left over x, and then the x squared off the 7x squared is a 7. So then the last two numbers we got to take out, but they're both negative. We're going to take out a negative, and I see 4 goes into 28, so I'm going to take out a 4. And when you take out a negative number, everything that's left inside is going to be positive. Or it's going to change sign, I guess, in this case. So this was a negative 28. Now it's a positive 7 because we took the negative out. So notice we have the x plus 7. We're then going to factor out that thing because they both have them in common. And what remains comes from the x squared minus 4. Those are what's left over. That's what's left over after we take out the x plus 7. Okay, so then we have x plus 7. And then the x squared minus 4, that's a difference of squares. So you have a square minus a square. This, it's going to be x plus 2, because 2 squared is 4, and x minus 2. Okay, you might need to review difference of squares. Okay, then we can sketch polynomials. We can put the zeros. Okay, we've got, I'm going to do these in my head. My zeros are negative 7, negative 2, positive 2. If you're wondering how I'm doing that so quickly, I'm just asking myself, what can you plug in that gives you 0? It's the opposite. Okay, so then you do 2, negative 2, negative 7. And just go up and then down. That was terrible. That's generally the shape. We don't know how high up and down it goes. All right. Go ahead and finish the rest of this. There's another type of factoring. You're gonna you can look at this example, but it's like a chunking. You're plugging in an x squared. I'll just show you this one real quick. So you could do, you can replace the x to the 4th with x squared squared. It's kind of like that chunking one we did earlier. Then you can replace it with a letter like y. Okay, then you can just factor it. 2 numbers that multiply to make 100, add to make negative 29, are negative 4 and negative 25. And then you replace the y. You put the x squared back. Right? The y was representing what the x squared that I plugged, that was there. And then they did difference of squares to factor a little bit further, and then they were done. All right, so that's factoring polynomials of higher order, so higher degree polynomials, and how to graph it. Don't forget there's the talk where you can summarize all of this. I hope that was helpful.